This is chapter 2, number 72. This is the rocket problem. This is one of my favorite problems. So they figure out how to launch this rocket with some initial velocity. They're either using a catapult system, or maybe it starts in a well and it's launched up. But you know, when it's at the ground, it's launched up and it's already moving at 80 meters per second. It's accelerating at 4 meters per second squared, which again means that for every second it's going to be increasing its velocity by 4 meters per second. And you know it actually does that for a distance of 1,000 meters. So you don't know the time yet, but you know it does this phase 1 for 1,000 meters. So let's just talk about this. With this, if you think about it, it's got a velocity, an acceleration, and a distance. To me, that leads us to the v-squared equation. So again, I would encourage you to write it down in the abstract. We don't know the final velocity. That's the goal of this particular relationship. We know the initial velocity is 80. We're accelerating at 4, and we do that for 1,000. So when we solve that for v squared, we get 120 meters per second. Well, I'm also interested in the time it took. Well, if you think about now, I have the velocity equation. I think this is something you probably could do in your head, but if you got to 120 meters per second and you started at 80, and for every second you increased your velocity by 4 meters per second, well, that's just 10. Every 10 seconds of an increase of 4 meters per second is going to be an increase of 40, and 40 makes 80 from 120. So you do get 10 seconds. Now let's go ahead and call this T1. So 10 seconds is this first phase. Then the rocket's engines stop. That doesn't mean that the object starts to fall. That just means the object enters free fall. And so now we're in a free fall zone. And so in phase 2, there's no thrust, so the velocity is up, and let's just call the initial velocity now 120 because that's what it's going at that moment. And the acceleration is negative g. So it's accelerating down, but it is still moving up. And what this acceleration is going to do, well, it's going to slow it down, and eventually it's going to stop. There's a variety of ways to attack this. I would just use the v-squared equation again, because if you think about what you have here, you have you want to know the distance that it gets to. Your final velocity is 0 because it does eventually stop. The initial velocity of this phase is the 120 minus 2. It is under the influence of gravity of 9.8, and then for how long? And when you solve this, you get something close to 734 meters. Now the question would be, what does this represent? This represents the distance of this deceleration. The actual height you're at, well, you started this at 1,000. And so your actual H max is 1734. If you wanted to do this in a different way, we could have used the position equation. Again, y equals y naught plus v naught t plus 1/2 at squared. Okay, and what we have here is that, excuse me, we don't have the time yet. We could have used the velocity equation to find the time. We know we're going to stop. We started at 120. We're going to slow down at 9.8 meters per second for a certain amount of time. So when you solve this, you should get 12.24 seconds. And that makes sense. Think about it again. You're roughly slowing down 10 meters per second every second. So how many tens do you need to slow down from 120? Well, 12. That's a little more than 12 because we're using 9.8 instead of 10. At this point, this is the time where you could have used into this equation to find the max height. This would have had the 1,000 built into it. So you could have said 1,000 plus going 120 for 12.24 seconds minus 1/2 g times 12.24 seconds squared. And that y actually would have given you the 1734 because it's got the 1,000 built into it. It's actually telling you the final position at 12 seconds, knowing that you were traveling 120 at the beginning of this particular phase. Okay, so now we have max height, and then we'll actually call that T2. That T2 represents when you're slowing down. And now we're kind of at the top. And we enter phase 3 of the motion. Now we're just going to fall. Variety of ways you can do it. If you just want to hit the ground, again, standard position equation applies. You want to hit the ground. You started at 1734, you had no initial velocity, and you're losing 1/2 gt squared. Now I wrote it like this just to show you what does this look like. Again, if most of you wanted to jump to just straight up using h equals 1/2 gt squared, I just want to remind you that this equation is the same thing as our standard position equation. We just rearranged it and just skipped some algebra steps. But realistically what you're doing is you're setting 1734 equal to 1/2 gt squared, just like you did if you would continue to solve this equation and you solve for that time. We'll call that t3. That's that free fall time. It ends up being something close to 18.82 seconds. If you want to know how fast you hit the ground with, and again it's just before you hit the ground how fast you're moving, the velocity equals v naught plus 18. Hopefully this makes sense that the final velocity, you wouldn't move in all at the beginning and you were losing 9.8 meters per second for that 18.82 seconds. And so your final velocity should be somewhere close to like a negative 184. If you wanted to use the v squared equation at the end, you could have jumped right to this. So just as another way, the v squared equation could have set a final velocity with an initial velocity of 0, falling at 9.8 meters per second for 1730 meters. This also would have found you that 184. This would have given you 184 because this is going to find you the magnitude, and then of course you know you're moving down, so you can put in the negative sign. But again, if you want to know the total time, then the total time is just the 10 plus the 12 plus the 18.82. Okay, so it looks like that total time, nope, sorry, 12.24, excuse me. So you get total time somewhere in the range of like 4106 seconds.